Hello, everybody. Let me fix this here. All right. Now, let's see if this works. We should be live, and you should be able to see me. All right. Welcome to a vacation stream. This is my first week of vacation, winter break, and I decided to keep working on implementing this paper here, which I've been, hacking on the last few weeks. So what you've seen in the previous streams was that I implemented the part of this paper that explains how to prepare for register allocation and which data structures are used, and how we can take our IR and turn it into correct form. This we did live on stream, generating moves for phi operands, which is an SSA thing. Then we did, I don't think we did this live on stream, but what we did for this is to compute the live in and live out sets of the IR of the CFG. And then in the last 2 or 3 weeks or something, I implemented this on my own, computing live intervals. So now all the bits and pieces are in place. Building the live intervals, we now know how long a var is live. That means how long it lives from its definition to its last use. Then I also implemented joining of values, which is something we need to do to say these values should go in the same register, especially important if we have phi functions in SSA. And then, I implement this. And then the next thing in the paper is the linear scale algorithm, which is the register allocator that puts stuff into registers. And that's where we are. So, hi Asbjorn, thank you. We'll have a good stream. I hope we will have a good stream. So this linear scan algorithm, I'm going to scroll down now, and you will see it's one page of pseudocode, right? And I was a bit scared of this. It looks scary, right? I pulled this out and reformatted it in my notes here, where you can see, I turn in like pseudocode JavaScript kind of thing, just so I get to next highlighting and I can see what happens in which loop and whatnot. So, it didn't look that scary anymore, except down here you have this stuff, assign memlock, which is this function that gets called when we are not able to find a register to put a value in, either because we ran out of registers or, it's not compatible, which is not the case that I'm worried about right now. So these are my notes. And then I started to implement this, just hacking on this. And actually, I think this morning I got it to work. So what you are about to see is my register allocator that kind of works. It is absolutely hacked together. I now want to clean up some of the code and understand it better, which means, looking into how we can do stuff better in Rust or not. So let me walk you through it. So this we did live on stream, generating moves of phi operands. Then we compute the live sets, giving us live in and live out sets. Then we number the instructions, which just means, let me show you. So numbering the instruction means this is a CFG. It says this here is the first one, this here is the second one, third one, or the other way around. This is currently unstable for me in my code, unstable sort, which is fine because it shouldn't matter, but just pointing it out. And then, 4, 5, 6. The reason why we want to number these, walking down the successor chain of this graph, is, of course, to be able to say the live interval of this value starts here and ends here. That is the first thing we want out of this. We could do this with pointers, of course. But the other thing that numbering gives us is to be able to say, I have 2 intervals. Which one starts first? Which one ends later, right? You have numbers you can compare. This, also possible to do with other stuff. other solutions, but what I tried to do was follow the paper as closely as possible and not deviate too much, even though it might not be rusty or it might not even be a good idea with my data structures. But so far it works. So yeah, number instructions. Then the next thing is compute life intervals, which is, I can show you, the test is pretty cool. Where is it? Life intervals, joining values. Oh yeah, it's in liveness. And then here in the tests, compute life intervals, diamond shape. So this is the thing from the paper on the right. And you will see down here that that's not super readable, but we basically say this value A lives from instruction 1 to 4 and then again from 1 to 11, right? So A is up here, 1 to 4. 4 is here because we number our terminators. So this is where it gets defined, and then where it's used. And then also from 10 to 11, I don't know, I have to look this, it's confusing, but this, I think this might be 10 and 11. Yeah, you get the idea. This is what life intervals are. And then we join values, which was pretty relatively simple, although it has a bit of a tricky thing in it where you say we're going to join values and going to merge their life intervals, which is what this paper does here, right? I can show you. So values are joined if they, match conditions. This is just what I put here. And then you merge the intervals, and then a value, like a unique name in the CFG, has a new representation, which is the value it was joined against, which is this thing which was involved in my light bulb moment this morning, because I implemented the final thing here, the linear scan algorithm. And again, it looks really nasty, where, this is basically this pseudocode on the right here. So we calculate the weights. This is what I did this morning. We calculate the weights of these values, which is, let me show you the official definition here. The weights of the intervals can be computed from the accesses to values and are as follows. So essentially, let me move this over here and let me show you the test case. So this is the thing that I implement. It essentially says, look, B is used 1 time here, 2 times over here, right? A, for example, is used also 2 times, 1 over here, and then over here. But this is a conditional thing, so it might only be used once. And, compared to, say, D or E, I think D is used often. No, it's not. B is used the most, which means it should go into registers, blah, 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 even though it might have a conflict. So this is what I built into this morning. And now this works. Like if I run this, you will see that the tests pass, but that is not so cool. But if I say put a panic here and run the tests again, so they fail, I get the output, right? You will see that these numbers are a little bit off right now. So because in the paper, they don't number terminators, which is just a fancy way to say the last instruction in a thing. So if I turn the numbering of terminators off and we look at the expected result, which is this figure over here, this graph, picture, whatever, over here, we can see that, these are the instructions. We have these up here too. We can see that it put 4 values, these, into registers and the rest on the stack. Also in the paper, it puts 4 things into registers, right? Register 1, register 1, register 2, register 1. Here you can also see what a register allocator does. This one, this value I5, which is the thing defined in instruction 5, which is this one here, which would be the D on the left. If this is in the RSI or, R1 register, that means that this one here cannot be in the same register because they share a lifetime. That means they're live at the same time. Okay, this is what the register allocator does. It says, all right, this function, there's X values involved. I only have N registers. Which of these X values do I put in which registers and for how long? And this is a really hard problem. There is no perfect solution for this. And a lot of algorithms are really complicated. And the problem is, or what makes it really hard is, well, let's not go into the theory of it because I cannot explain this, but to give you a practical example, we're talking about a real machine here, so you have a number of restricted registers, but not all of these registers are equal, right? On x86, you have the EAX or RAX register, which is where the return value goes. So it's not up for grabs. You can't just use this for any value. If you return from a function, the return value needs to be in that register. So you need to take that into account, which, by the way, I have not done this yet. The other thing is, on x86, params go into registers, to specific registers. So your register allocator also needs to take this into account. And then you have all of these constraints, and now you still have local values, and you still need to put them into registers or on the stack. How do you do this? And this one here does it by saying, of course, it's linear scan, so it walks through the intervals, starting with the first one, and then puts them or assigns them to registers. It allocates them, and if it cannot find a register for those, it puts them on the stack. And what this also does is this thing that I highlighted over here. It takes into account that the value that is used more often should be in a register, even compared to another value that is not used as often. So what I got working this morning is basically that this, before I got it working, this had B in it and not D, I think, in registers. But what this code then does, this is B, right? I2. It says, no, the others are used more often, so they need to go into registers. And, I got this working. Now the test pass. Is this Advent of Code for Day 26? No, it's not. I gave up on Advent of Code. It's too stressful for me. So yeah, that's where we are. It kind of works. I think it works at least in a way that it puts stuff here, like it said, like it says in the paper, into registers or not. And we can just now, before we dive into refactoring, we can double check this, right? So I1, right? That is, in our case, let's see, I1, that's 1011, that's A, should be in one register. And it is, one is in RSI. Then I2 should be on the stack in memory, which it is. It's over here. I4 should be in a register. It should be in the same register as I1 because the lifetimes of I1 and I4 do not overlap, as you can see here. This one lives from 1 to 3, then the other one lives from 4 to 6, and then the first one lives from 8 to 9. But then we get to I5, and I5 overlaps here, 5, 6, with 4, so they cannot be in the same register, which is why I5 should be in another register, R2. So this is it. This is I5, 4002, I5. Yep, this is this one here. This should be D. Yep. And then the last one that should be in the register is I12, 55, that is E, right? So it's a bit hard to see. That's why I put all of these constants in here, so I know where I am. Like if I see 22, I know, okay, this is B over here. All right, so that looks good. That looks like it works. The question is, did we get this right with the weights? It says here, interval 2 was put into memory because its weight is less than the accumulated weights of intervals 1 and 4 that occupy the same register at that time. So interval 2, this is this one, right? So, okay, so basically our allocator says, hey, should I put this one into memory or in a register? And then it says, oh, there's another interval overlapping, which is I1, right? And it says intervals 1 and 4, they are in the same register at the same time and of the current interval. So let's see how this works, because I really blindly implemented this. So first of all, here's how I calculate the weights. So this is really like 80% of this compiler are loops, like just looping over stuff. So what we do here is we go over the function that we're currently looking at. We're looking at each block, which are these things in the control flow graph with instructions. And in each one, we take a look at which values it reads, right? So this says instruction reads back here. And an instruction read is just, say, the parameters, or like the on the left of this arrow in each instruction, you'll find a target. This is where an instruction puts a value. And on the right-hand side, you will see the operands. So here you can see this instruction reads this value. This one here reads this value. A phi instruction reads these two values. This one here, a binary instruction, like with a plus, it reads two values. This one here reads one, right? So what we're doing here is we say, for each instruction, give me the reads, flatten this. For each read, give me the place, which, you know, in this case, reads returns vars, which is saying a block and a place, which we do not really care about. So we just, you know, we should maybe this is what we should do. Instead of, so what we get back here are vars, which is a block and place, and we throw that away and say, just give me the place of this. And then here comes the interesting bit. Then we say, give me the representation of this value. So if it says here 4001, we say, what is the rep of this? And down here we say, you know, we have all of the rep is the thing that I mentioned earlier, where we joined values. It's this little function, which looks actually pretty nice, and Russ later showed you. So it says, is this value, like this place, is it joined with another one? Do we have this? All right, so then give me the rep of that value. So it's recursive. But if we don't have a joint value, just return the place. Okay, so in the case of, I don't know, let's say 4001, right? It would look into this joint thing, which I printed here for debugging purposes, and see, oh, there's no key 4001, so it returns 4001. In the case of 4002, it would return this one, okay? And the reason why I use this when calculating the weights is because it doesn't work without it, but also we merge these intervals and they're merged on this rep of each place. Okay, so it just wouldn't work if I remove this, because we would not be able to, we would talk on two different data layers. The intervals are only using these reps, and we have more places than we have intervals, as you can see here. Like we have a lot of places, which are all the numbers on the left of the arrow up here. And we only have 1, 2, 3, 4, 5 intervals. And these intervals are hidden or associated with the representation of each value. So this is what we need to do here. And then blah, blah, blah. This is now, let's scroll through this. This we can make better. What you see here on the left is now this. We give, we get all the intervals that are in this function, which are these 5. We also get the places that don't have an interval, which are basically dead code, because they are, they don't have an interval. That means they are defined but not used at some point, so they're only defined. Then we take this little helper struct and say for each value that did not have an interval, we just put it on the stack. Then this is, now really close to the paper. We build up our data structures. Oops. Oh, I can scroll with J and K in the PDF viewer. That's nice. Active, inactive handle, which are all things that this algorithm uses for intervals. Then we say, what are all the free registers that we have available to us? By the way, I only use 2 registers because the paper only uses 2. If I comment more in, you will see that the register allocator puts more stuff in registers. And then, it says, all right, what's the first one? Unhandled is our work list. And it says, give me the first one in unhandled. Then it removes the active intervals that expired. So now we're looking at another one, and we say active, did it already end before the one we're currently looking at? Then we put it in handle and remove it from active. And if it was assigned register, we put that register back in our list of free registers. If not, and the intervals of an active one overlap, do not overlap with this. We put it in inactive, remove it from active, and take the thing out. So this we can make better. This is just there's a function, a method for this, where we basically filter or drain this hash set. So we don't need to do this. Then we remove these from active. We do the same with inactive. Check for inactive intervals that expired or become reactivated, which is nope. It's up here. It's this in the paper. And we do the same thing, right? This is the comment. If I ends before the beginning of the current interval, we move I to handled. If I overlaps with the current beginning, we move it to active and remove the register from free, because we know it's not free. Like, we cannot use the register anymore. So now we know which registers are still free, or we try to collect them. And now we say for all the inactive intervals that overlap with current, we remove the register from the list of free ones. For each fixed interval in unhandled that overlaps current, fixed, by the way, I have not implemented yet. Fixed is exactly what I mentioned at the beginning. It is when we know beforehand that a certain instruction needs to use a certain register. So, parameters, for example, we know that they must be or will be in a specific register. So here you basically say, all right, if like the unhandled ones, these are the intervals we still need to look at, but if they are fixed and they already have register, we also need to look at them now. That overlaps, right? So this basically we don't need to do now. Basically it does this loop, but then this here will say, nope, there's nothing assigned yet. And then we need to assign register. If there's no register left, we must do assign memlock. And to fight the borrow checker, I put everything in here. Let's skip this. Otherwise, we say, does our current interval not have a register yet? Then it picks one from the registers in F. It removes it from the free list and it moves current to active. So that's the happy path when we have a register available. The non-happy path is we don't have register available. So what do we need to do? We now look at all the weights, right? This is what we just talked about. We say for all, this is the comment from pseudocode, for all registers, set their weight to 0, which is why I create this new hash map. And we take all of the registers, and then we say for all intervals in active, inactive, and fixed unhandled, which are these, if their interval overlaps with current intervals, increase their weight, basically register the weight, and then find the one with the most minimum weight if the weight of the interval that we want to place is smaller than the weight of the register that is already used. So we're saying, hey, I have a new instruction that I need to, or I have a new value that I need to put in registers. Its weight is current weight. But I don't have any free registers, so give me all of the registers, sort them by their weight, that means their combined axes, and give me the one with the smallest weight. And if my weight is smaller than this one, I put it on the stack. But if my interval has a bigger weight, it's accessed more often than the register as it is now, or would be used, we remove all, we basically take all the intervals that we assign to that register out and put ours in. And we say, look, give me the active intervals that have this register assigned to them. Remove them from active. Remove them also from inactive. This is just duplicated code, by the way. We can combine this. Yeah, we should. The problem is this. Oh, nice. Chris Fowler has a nice blog post on testing register allocators. Yep. I will need to take a look at this. Who does Rust 6 freaking a.m.? I do Rust at 6 freaking a.m. But right now it's not 6 a.m. for me. It's 3 in the afternoon. And then we signed this, blah, 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 blah. So as you saw, this code is horrible, okay? So before we go any further, what I want to do is I really want to clean up some of that. And for that, we need to run the tests and make sure that works. For that, we do full screen and just see. So first thing I want to do is this. Maybe not that. This we can remove because I already fixed this. This I think we can remove. So this I want to make a parameter because then it's easier to test. I basically want to say run linear scan, and these are the free registers. Yep. Let's do this. So we put in reg codegen reg. This is this the default GNOME terminal or Kitty? This is Kitty. Please let me know if the font is too small. Do you know coding? I think I do. I like to think I do. All right. So we take free out. Then up here, we put it in. Does this work? Can't find macro. Yep. Then we put this in here, all registers. All right, what is the problem? Cannot borrow free as mutable. Can we not say? Why does this not work? Let mute free. Why? Let free registers. Codegen reg. Let's take RSI and R. Okay. Why did a black thing appear here? Now it's gone. Free registers into. Do I need to put in? Yep. Let's make this a mute. Why do I need to put in reference if this consumes it? Can I not say? Oh, just like this? Yes, amazing. All right, cool. So now we're getting closer to be able to test this. So ignore all of the debug stuff. What we have here is we basically set up our whole thing. We do all of the preparation, then debug printing, blah, blah, blah. We can, put this in a block so it looks a bit different. Same here. All right, so this is all debug stuff. Then we say, do the linear scan algorithm, and these are the free registers you have available. And then we do our assertions and say, hey, we now should have memory locations for this func, and in registers should be A, C, D, and E. And assert on stack is the temp stuff, and importantly, B. All right, so that means, does everything still pass? It does not, because I turned the number instructions, I turned the numbering of terminators off. So let's see. Yep. All right, gonna make some tiny commits. And we're gonna say make free res a param to linear scan. All right, so this will come in handy. The other thing that I want to fix is, isn't there like a Rust thing where we can say while blah 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 first is some or something? I think I have a while loop somewhere else. While let. This is exactly what I want. Work list pop. But unhandled. What is unhandled? Unhandled is a vector, and we need to remove the first one. Doesn't Rust vector pop first? Does this exist? Is this a thing? Remove first. No. What does remove 0 do? If it doesn't have an thing left. Panics if index is out of bounds, yeah. That's what I figured. Push, shrink to, swap, remove, pop. Yeah, I want something that removes the first one. Yes, vectic. Yes, that's a good. Yes, thank you. Yes, let's do this. That's perfect. Where is it? I used that too somewhere. Yeah, here. When I do. Yes, when I. This is for traversal of the CFG, so this is the same thing. Push front. Yeah, I have a bunch of these. To visit. Pop front. There you go. Pop front. What we need. All right. So, functions. We can also rename this. This is a stupid name. DQ. Boom. Cannot import. Let's go. Place intervals. Place intervals. No, we don't want to push back. Sort. Oh boy. Oh, we need to sort. Rust like DQ. It doesn't sort, right? Maybe. Maybe that's not worth it. We could keep it a vector and sort and then put it in. But that just seems. Maybe that's not worth it. Yeah. So if we do this, we can still say, does it do this? Yeah. So now it returns a vec DQ. And then we can say while let cur sum cur equals unhandled pop front. Yep. Okay. I like this because this looks really clean. I'm not sure whether what the Rust compiler does with this. Like, whether it requires another allocation. Oh, this avoids reallocating where possible, but the condition for that are strict and subject to change, so shouldn't be relied upon unless came from vector and hasn't been reallocated. Well, let's just keep it. I mean, honestly, I'm not worried about performance in this. So yeah, we have without intervals, it's a vec. These are the intervals. Found, this is just so, since we used the target rep, yeah. All right, let's go back up. This, by the way, we can remove. Let's rename this and call it build work list for linear scan. Let's rename this and call it build linear scan work list. That's cool. Okay. So then we can maybe extract this up here and say fn calculate place weights. And we're taking context, which is the context, and the func, which is our block func. And it returns a hash map of place in I32, I think. Like this. And then up here, we can say weights, calculate place weights, context func. All right. We can rename this and call it calc place weights. All right. Then we take this one. And we call it reads var. And then we copy and paste this and call it reads places. And here we only want the places. And then phi operands. What is phi operands? Oh yeah. So we can remove this. map VV place. What is ops? So it's already vac. This is found to be of type cloned map. Yeah, I need a collect. No. Clone. The value of terminal cannot be bound. Why does it need to be in okay. Oh, is there not filter map? Flatten. That could probably be made better. Alright, what warnings do we have? It's not used. Alright, so let's go to our reg alloc. Reads places. Call it. Alright. No method name, yep. So we don't need, well, we don't need this anymore. Reads places. Oh yeah, it doesn't take an argument anymore. Unused var, yep, here you go. Map move I reads places, flatten. Yes. Alright. Are the tests still running? Yep. Let's do another tiny commit. Rename stuff, extract stuff, move stuff. Future me will be thankful. All right, so I'm staring at this because it's a kind of thorn in, like, look at this. Like, it could be a method on context. This we can remove because it was correct. because this is just so convoluted. The problem is defining stuff. Like I have this big data structure. It's kind of modeled after this Thai data structure that the Rust compiler has. It is basically the whole context that gets built up in the compiler. And it has a lot of data in it. And since it has a lot of data in it, that means context is always being passed around, like here, right? It's always context and func, context and func, context in place. So, but I barely have any methods to access the data defined on this, because it always, either the passes that use the data also build it up, or they only want to access that data, and then you get into like borrow checker stuff, because sometimes you then need to take a reference to the whole context, but it requires a mutable one, blah blah blah. But what would this feel like if we say play hello, me wondering, if we say place rep, and it takes in self and a place, of course, and it returns I'm fine, how are you? It returns this, and then it says match, match, what am I doing? Self, joint values, self, place rep. Yeah, you can't get into the Christmas vibe. I'm sorry for you. I have to say, this year I am in the Christmas vibe, but it's mostly because I have a 4-year-old daughter that is really excited about Christmas. And she really likes her Advent calendar, and she really likes the tree, and she's incredibly excited for Christmas. So, yeah. Get a kid. So, what does this feel like? It's not too bad. It's not too bad. All right, that's not too bad. Wait a second, before we commit this. little comment. Okay. Tiny wrap. All right. So what else do we need to clean up? Oh yeah, this whole active thing. So this is a bit nasty in that we iterate over active, and then depending on which conditions are true, we remove stuff from active by adding it to another hash set, and then going over that and removing stuff again. I think Rust has something else that allows us to retain. Yep. So retains only the elements specified by the predicate if it returns false. All right, so we can do this. So we say active retain pi false true. Yes. So, okay, is there a way to make this a bit easier to read? What if we do something like this? Let's say we have a closure that says move and free reg, and it takes in a set. It takes in the place interval and a set. And what it does is set insert. Oh boy. Lifetimes, baby. Oh boy. fuck do I declare lifetime? Rust closure lifetime. Oh, this would be so cool. Let's leave the duplication for now. Let's refactor this and say inactive retain pi false, false, else true. Yep. Can you do a match? Let's do this. No. Okay, why did my undo break? I don't like these literals here, I have to say. But, well. Is there an opposite of retain? Remove. No. Take. What is drain filter? Oh, it's experimental. Ah, that would be it. Well. Okay. That is some weird go. Absolutely. It's a new generics go. Okay, unhandled fix. All right. Let's do this and say refactor removal from, what was it? Active, inactive lists. So now what I would love to do, we can remove these comments, I think. Can remove this. Can remove this. Yeah, so this I would love to pull out in a function. Let's try. Oh, there's a bug. Let's fix this bug first. Here, this is all registers. Aha, okay, okay, this is interesting. So, free, where's the, are you enjoying Rust more than Go for compilers work? Complicated answer. On the one hand, I really like having enums, and I do like a lot of the tooling around Rust, and I do like a lot of the small little helpers, and I do like macros, which make it easy to often write easy to read tests. What I find really hard about writing compilers in Rust is the borrow checker, and because I have a lot of graph data structures where you have references, nested references, and and you need to mutate them. You need to walk along the graph. You need to mutate them. You need to remove stuff. You're walking on all of the instructions. You replace operands because you renamed them somewhere else. And that is really hard to do in Rust if you go by all of your instincts that you build up doing this in other languages and say, all right, I got a graph, so I have a root node, and that has two child nodes, and those have child nodes and whatever, and I'm going to walk them down, and then if I find the right one, I'm going to replace it. But that doesn't work, because in Rust you cannot have a reference to this one while you mutate this other one, and you've clashed. So you end up taking the reference part out and for example, putting it into IDs or indexes or whatever, which is what I do here. And then you walk those along so you don't hold a reference to one part of the data structure while modifying another part. And that can be really cumbersome. But I got kind of used to it, as you see here. Like, I just start putting all of the stuff in different hash sets, right? Like this. This could just be, references or something, and I'm, completely not even trying that anymore, to have pointers somewhere where they live long. Yeah. So here we clone this. And then all available register. Here. Bug removed. Cargo test. So let me give you an example of what is tough in Rust. So I have this, which allows me to traverse my control flow graph. First of all, if you don't like generics, you're gonna hurt your eyes looking at this. But if you look at, let's see where it is. So this builds the DOM tree. Let's see. So you have a lot of this stuff where you always build up new intermediate structures because you need to sort stuff and you cannot hold other stuff. But that's actually not the example I was looking for. So if I look at SSA, insert 5 functions, 5. Oh yeah, there it is, right? So this, we're saying we're walking over all of the blocks or some of the blocks in a function by going through all of the assignments and see whether they have two parents. Doesn't matter. The point is, I'm working the blocks of this CFG. I'm walking through the CFG. I have a block here. And then I walk over the DOM frontier of this. And then I want to insert a 5 function into one of these blocks. But that is not easy, because in order to insert something into a block, I need to have a mutable reference on it, and the block is owned by the func. If you look at the if you look at this, it has blocks, right? This is one of the first data structures that I wrote in this. I cannot just do this and say, func blocks df block ID instructions push whatever this is, right? Say we comment this out and go back and do this. Right? It says consider borrowing here, okay. But then consider blah blah blah. Then we don't need this. We don't need this. But then it says cannot borrow data and index as mutable is required, but it's not. So we say, all right, get mute, and then we put the ID in. But now we do an unwrap. And then there you go. It says cannot borrow func blocks as mutable because it's also borrowed as immutable. Because, right, you put another thing into the work list, blah, 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 blah. So then you start thinking around all of this, and you start with IDs and other stuff. And I get why this is a thing. It's just hard because all of the algorithms that in SAW, where something traverses something else, do not work like they do. Like if this is just like, I wrote down the pseudocode as I got it from a paper, for example, and then you run into these issues and you need to translate it back and forth, and then you bump your head against it. Then what you end up with works, and yes, it might be more performant even because of data-driven design where you put stuff next to each other, blah blah blah. But it just doesn't look like the original thing. And I think Rust people often underplay the cost of that code just looks completely different, or it is organized in a different way that is not immediately visible to somebody reading the code. It's just, why does he have this immediate data structure here? Why does he collect this? Why doesn't he do this? And only when you really dig in, you realize, oh, it's because of the borrow checker. How does the Rust compiler deal with these kind of issues? As far as I know, it deals with them exactly as I do, except better. They use, arena allocators. They use these IDs into vectors. Like, there's a bunch of strategies you can use, which I also use, right? Like, so they have this thing that looks close to, where is the context? No, it's in the middle. There it is. So this thing, Rust, has this data structure is representing guides. Where is it? Rust tie, middle tie. Where's the source? There's something. Come, Rust, lang, Rust. Let's see. I'm not sure how I get to the right thing. Middle tie documentation. Is this it? I think this might be it. So the point, what I'm looking for is they have a data structure that they pass around through a lot of passes in the compiler, and they have these accessor functions, getters and setters. I think it's the tie data structure, but I'm not sure. Tie implementation is actually tie. You can ignore tie. You will basically never tie as the only exception is to the tie can. Tie also has two more fields there. So that allocating and working with it's this one. The tie context. There it is. So types is underplaying it a bit. Let me look in my notes. No. This is what we were just looking at. True can control. There you go. Rust MRI. Rust MRI. This is a local reference. Oh yeah, so yeah, okay, so this is the equivalent of my IR. Alright, so they have basic blocks. This is basically, yep, it says here, of a single function. And then they have scopes, return type, var declarations, var architecture, blah, blah, blah. But this is not a lot. It's just, they have more, and it's on other types that they pass around. Basic block. What does a basic block have? Yeah, the basic block is just... Oh, this is the ID. Okay, where's basic block? Basic block data. Okay, so they do the same thing. So they don't have a reference. They say basic block is just an ID. And it's an index into the basic block lists of the MRI, which is smarter than what I do. I use a hash map and generate IDs. But that allows me to have global identifiers across multiple functions, and I don't have clashes. And yeah, you have statements and a terminator statements. Yeah. All right. Back to it. Okay, so we wanted to extract all of the stuff in here, right? So now let me try some weird tactic, which I call winging it. We call this assign memlock. We're going to put the bunch of stuff in here. And then we say, we see what it needs, right? So it says active should be a hash set to a place interval. Inactive should be a hash set place interval. It should have, Jesus, all available registers should be what? A vec of cogent reg, yep. Then we need cur, which is our current interval that we're looking at. We need mem, which is memory locations. And we need the weights, which is a hash map of place and I32, I think. And handled, which is the same thing here. This is a long ass thing. And of course we need a context, right? Poof. Oof. Cur, we don't even need this. Oh boy. Why does it, these two types? These two types are declared with different lifetimes, but data throws into handled here and throws into active. But they all have the same lifetime. But cur, what is cur? Cur is not a pointer, right? No, it's not. Do I need to make it a pointer? Oh! But I don't want it to be a pointer. Lifetime mismatch, of course. Of course. Aha. Like this. Oh. This function has too many arguments. You're right. You're right. You are right. You're right. So wait a second. Can I now not... I can remove this, right? And then do this. Yeah, so I'm thinking this, like what I would love to have is a data structure that contains all of these. So we just have to pass one thing and then we can say add to active, add to inactive or something. But yes, let's see. Assign memlock. Context. All available registers. Mute active. Mute inactive. Mute handled. Cur. Mute mem. And wait, this needs to be reference weights. All available registers. Oh yeah, yeah, it's a hash set. Nope, this needs to be a borrow. Cannot. Oh boy. But why? But it's in a different thing. Like I don't borrow it. Immutable more. What? But that is... I cannot borrow it as immutable up here. Yeah. But I don't... What? That's just a different scope, is it not? If I do an iter cloned... Oh boy. Yeah, this is what... Alright, let's... This is... I don't like this. Let's move it back. I also don't like this, by the way, for the record. We need to find something else. Another way of organizing this data. Because this is too much fighting. So these are the reg weights. Does this work? It's like Ruby in Ruby and Rust. All right. For I active, if I overlaps, we can do a filter here and say int intervals overlap occur intervals. I'll remove this. These are active and inactive. To do include fixed unhandled once we have handled. Yep. Find R such that WR is the minimum. Let's rename this reg candidate. This should not be necessary, I think. Because we only build intervals for the reps, so hmm. 189 198. Weights. Because we built the weights up. I see. Is there a Rust version of the interpreter and compiler book incoming? No. No, there's nothing planned, or I don't have any plans. It just, my Rust is not too good to publish something. And frankly, it would be too long. Assign memory location. Remove from. Oh, this is. We can refactor this and say active. Retain. Int. What are your general thoughts on Rust? You need to watch the recording and jump back 20 minutes. I'm just excited. Short version, I'm not super over the moon with it, but I'm starting to like it. But I think it's yeah. I think it's not the silver bullet and the most enjoyable language that a lot of people say it is. Rust pattern matching. Give me the syntax, because I think there's a way to move my condition in there where we can say if no match control file. Isn't there? There you go. Oh, we were. There you go. binding, wildcard, rest, range, structs, tuple. Rest, match, pattern, if. I think there's some way. Isn't it just this? Yeah. Yes. Ooh, ooh, ooh. Let's rename this PI because that's what we did up there too. And then we remove it from the registers and add it to the stack. All right, then we can do the same. And instead of active, it's inactive. Is there maybe a way we can define that closure? What? Yeah, so. If I use this, no, it doesn't work. God damn it. I thought it was easy, would be easy. Oops. Whoa. Something with undo and formatting. Yep. mem assign active insert. What does the pseudocode say on this? Assignment relocations. Move all active. How do you manage to get free time for coding in the afternoon from your family if you are on holiday? Asking from a friend. I asked them and I said, I want to stream in the afternoons when I'm on vacation. And my wife said, sure. The weight of the So this is, we are here. Free, remove from free. If correct, then any register in F. Yep, so basically this says if we don't have a register assigned, then take any one. Haha, but wait a second. So if we have reg, this is actually a bug. No, it's not. It is. Hello, Rex Rove. Good to see you. Okay, so this is a bug because what this code here says is if we don't have a register assigned to our current interval, then take any one of F. And then remove that from free and move cur to active. But what I do here is I take a register from F and then remove it from free. But if it was assigned something else, then I still remove the other one, which is the bug. So let's say match mem get reg cur plays a sum reg. If there was something, then return that. Otherwise, we take one and assign it and return that. So then we have this. So we say, do we already have a register assigned to current interval? Then we return this. Otherwise, we take one from F, assign it to cur, and use that. Yep. And then remove it. And test should still pass. All right. More cleanup. All right. So the other thing I want to explore is if we could maybe put all of these in a struct, and we say struct linear scan context. I don't know, making stuff up, and it has all of these. Lifetime. Oops. Impl linear scan context. FNU. Self. Yeah, so we could move this, but then this other stuff wouldn't work, right? We could try. We say let linear scan context, linear scan context, new. Of course, that has to be mute. Say linear scan. That's just a lot. I wish I could get rid of this. All right, let's see what the borrow checker says. Boom. There it is. First mutable borrow cannot borrow. Oh boy. Second mutable borrow cannot borrow as mutable more than once. Oof. Yeah, so this is my problem with Rust, that you cannot just syntactically move code because the semantics are so tricky. So you think, oh, I have this bunch of, data that always goes together. Let's group that in another data structure. but then they are owned by the data structure, which changes how you handle the data. First mutable borrow of CX. Okay, so this is exactly the problem that I described earlier. So I put all of them in the same data structure now, but I also mutate the child data structures. I mutate active, which takes a mutable borrow of the linear scan context, and I mutate handled and inactive. So for the Rust borrow checker, it looks like, buddy, you're mutating the same data structure at the same time in 3 different places. That's not possible. But what we did before, where we had 3 different hash sets, the borrow checker would see that I access them at different times, right? And then they have different lifetimes. So this is a dead end somehow. Yeah. This was not a good idea. All right. Also coming close to the end of this because I need to hop off. But I do want to stream tomorrow. So what are the other to-dos? More tests and making it easier to test this. Somehow splitting up this bit of code. It's how many lines is it? 180 lines, one function. And there's a lot of duplicate code like this. It's the exact same thing, except, yeah. So even, can I not say, for set in active, inactive, set that works. That's cool. Do I need a vec? Nah. All right, nice. Okay. All right. So that's how many lines? 19 deletions. Fair enough. All right. Now, let's see if we can use that same trick up here. Nah, these are slightly different. Different enough that I think putting them together could be dangerous. We can remove this though. Can't we do... What does the algorithm say? It says... For each interval in I inactive that overlaps for each fixed interval in unhandled. So we could say... Can't we say iter chain unhandled here? Yep. Yep. Alright, that's easier. I mean, we don't even need to implement fix because we check it here. This says, is there register assigned to one of the intervals? All right. Yep. Isn't there like a filter map? PI. Looking at how you do this stuff makes you want to go and get your book about compilers. Would you say that there are any specific prerequisites? I do code a bit, mostly in Node and PHP, but I feel like I might lack in some theory departments. By a bit, I meant I professionally code for the past 6 to 7 years. Don't worry about theory. So if you look at Interpreter Book, there's a free sample here. Free sample. If you can make sense of that, and if you can read this Go code and translate it into Node or PHP or whatever it is you want to use, you are good to go. It doesn't get any harder than this. I specifically don't go into a lot of theory in the books because I myself am not a theory person. So the whole point of the book is actually, let's go from 0 lines to, I don't know how many it is in the end, 2,000, 3,000, and just write the code and learn by doing, and always start with the problem. Hey, we want to implement this. How would you do this? This is how we do it. We start with tests. Each test fails. So we do TDD in the book. And really, like if you don't have any theoretical knowledge about interpreters or compilers, this is why I wrote the book, basically, because I didn't have any theoretical knowledge. And, you know, taking a step back, in general, I learn better by trying something, bumping my head against something, learning more theory, applying this, bumping the next thing, learning something, applying it, bumping into the next thing. I don't read another book and then start doing something. It doesn't work for me. And also, I'm going to save the rant here, but I do think that most textbooks and papers are not meant to educate a beginner. They are mostly there to collect and share knowledge, but they are the Dragon book, the compiler textbook, it is not meant to be a book that a person that has never written a compiler before can read through from beginning to end and end up with a working compiler. The book is meant as a textbook for a college course or university course. It is meant to be accompanied by lectures and, what do you call it, like exercises and assignments and, teaching assistants helping out. And yeah. How long did it take for you to write the whole book? I think the first book, like a year, I guess. 3/4 of a year. So the first part was basically writing the interpreter, and then came the writing and ripping apart the interpreter and building it up and reorganizing the code and thinking about how do I actually build up this code base so that I don't have to jump back and forth in the book. So everything builds on top of each other without a lot of revisions. So yeah, a year, I guess, and the second one too. All right. Available registers. Kind of file value reg in the scope. Blah, blah, blah. So I thought that filter map would do this. Creates that both filters and maps. Filter map can map more concise. Oh. Nice. We already have this. We can use the same filter map up here. No, we can't use this. Do-do-do. All right, so you're watching me type comments, which I could have read out loud. I'm sorry. But I finally get it. Yes, so we can remove this. This we already talked about, right? Everything should pass still, I guess. Yep. All right, so we say cleanup and a few comments. Cool. So let's do, before I hop off and see you tomorrow, let's do one last test. And that is, if we do if we add more registers and say we have, I don't know, oops, whoa, whoa, what happened here? What is this? Now we have more available. We say RDX. No, what is it? Let's do RDI. Then we should have more values in registers, and this should break. Yep. Panicked at 2000 not spilled to stack, and 2000 is 2000 should be B. Should be B. Let's see where it is. B 2000. Yep. There you go. All right. And if we say we don't have any registers available, this. Let's remove this. Let's remove this. Let's say we have no registers available. Then nothing should be registers, and everything should be on the stack. Assert mem registers len. Oh, is empty. Is empty. Why is my highlighting so broken? Panicked. Register allocator 177. Unwrap. I see. I see. That's interesting. So let's remove the unwrap. If candidate, don't we have Rust option? Why do I not see? What the hell? And where's the? This one. Okay. So we could say match candidate sum candidate reg candidate weight if oh wait a second, where does this come from? Isn't that a typo? Yeah. Match if curl weight candidate weight Oh, okay. We need to change this. This is getting too tricky. So this is, yeah. Say if let reg candidate reg weight sum do this. Otherwise, if there's no register available, even we add our current interval to the stack. All right. So this also passed. So if we don't have any available free registers, everything gets put on the stack. That's pretty cool. So that's cool. Yeah. We could then, this we will do tomorrow. We could add another test. Ensure that if a register has been allocated, it's the intervals that use the register do not overlap. That we can do tomorrow. All right, make commit, clean up, add more tests. See ya. All right, and with that, thank you for watching, and I will most likely be streaming again tomorrow afternoon at around the same time, 2:30 in the afternoon in the CET, and maybe see you then. Bye bye.